Chip War, The Fight for the World's Most Critical Technology by Chris Miller. Picture this. It's August 2020, and you're standing on the deck of the American destroyer, the Mustin, as it cuts through the dark waters of the Taiwan Strait. A massive 5-inch gun points south like a warning finger. On one side, mainland China's sprawling coastline stretches as far as you can see, dotted with some of the busiest ports on the planet. On the other, the lush mountains of Taiwan rise from the sea. Up on deck, sailors are scanning the horizon, tracking the endless stream of cargo ships hauling goods from Asian factories to the rest of the world. But deep in the belly of the ship, in a dimly lit room, bathed in the blue glow of computer screens, another crew is watching something completely different. They're monitoring data flowing in from planes, drones, and satellites, tracking every movement across the vast Indo-Pacific. This warship isn't just floating steel and firepower. It's a technological marvel, packed with computerized weapons and missile launchers that can hit targets hundreds of miles away with the precision of a surgeon's scalpel. You'd think a ship like this would be the ultimate flex of power, right? But here's the twist. On that particular day, the leaders in Beijing weren't worried about the ship's missiles. They were worried about something you could barely see without a microscope. They were worried about a tiny slice of silicon. Welcome to the world Chris Miller reveals in his game-changing book, Chip War. This isn't a world where battles are won with missiles and tanks. It's a world where the real power lies in microchips. And trust me, this book has been called one of the most important of our time for a reason. It pulls back the curtain on the single most critical technology on our planet, the semiconductor chip. Today we're diving deep into this story, and by the end, I guarantee you'll never look at your phone, your laptop, or even the geopolitics on the evening news the same way again. You'll understand how this tiny, almost magical piece of technology dictates the price of your gadgets, the strength of your nation's military, and the entire shape of our modern world. You'll see the secret circuitry connecting us all, and you'll discover who really holds the power in the 21st century. This isn't just a tech story. It's the story of our time. Our journey begins not in the sleek laboratories of Silicon Valley, but in the rubble of World War II. That war was all about steel and aluminum, about who could churn out more tanks and planes. Whoever had the bigger factories won. But even then, a handful of visionaries saw something different coming. They saw that the next great conflict wouldn't be won by brute strength, but by intelligence, by machines that could think. Back then, a thinking machine sounded like pure science fiction. The most advanced computer, the U.S. Army's ENIAC, was an absolute monster. Imagine a machine filling an entire room, packed with 18,000 vacuum tubes, each one the size of your fist, glowing like old-fashioned light bulbs. It was brilliant for its time, able to calculate artillery trajectories faster than any team of humans. But it was also clunky and temperamental. The tubes burned out constantly, and because they ran so hot and bright, they attracted moths. Engineers literally had to debug the machine by removing dead insects. If computing was going to change the world, we desperately needed something better than vacuum tubes. We needed something smaller, faster, and way more reliable. The answer came from a strange class of materials called semiconductors. Most stuff is simple. It either conducts electricity, like copper wire, or blocks it, like glass. But semiconductors, especially silicon, are different. They're shapeshifters. You can coax them to act as both. In 1947, at a legendary research center called Bell Labs, 3 scientists created the first working transistor. John Bardeen and Walter Brattain were brilliant, and William Shockley was notoriously difficult but equally genius. Their transistor was a tiny device made from semiconductor material that could act like a switch, flipping an electrical current on or off. An on state could represent the number 1, and an off state could represent 0. With just ones and zeros, you can create the language of all digital computing. This was the breakthrough the world desperately needed. But the transistor was just step 1. The real revolution happened about a decade later, almost simultaneously, in 2 different labs. In Texas, a quiet but brilliant engineer at Texas Instruments named Jack Kilby was wrestling with the tyranny of numbers. Even with transistors, building complex electronics meant hand-wiring thousands of them together. It was a tangled nightmare. Kilby had a wild idea. What if you could build all the parts of a circuit, the transistors, the resistors, everything, not as separate pieces, but carved out of a single, solid block of semiconductor material? In 1958, he built the world's first integrated circuit. It became known simply as the chip. Meanwhile, out in a sleepy California town called Palo Alto, a charismatic visionary named Bob Noyce had a similar lightning bolt of insight. Noyce was one of a group of brilliant young engineers who had quit working for the impossible William Shockley to start their own company, Fairchild Semiconductor. This rebellious group, later dubbed the Traitorous Eight, basically founded Silicon Valley. Noyce's version of the integrated circuit was even more elegant. He figured out how to build the transistors right into the silicon and then print tiny metal wires directly on top to connect them. No more hand-soldering wires at all. It was a complete, self-contained circuit on a single chip. Pure genius, right? But here's the catch. In 1961, a cutting-edge chip held just 4 transistors, and making them was insanely expensive. Who would possibly buy this? Noyce and Kilby had built a revolutionary engine, but they had no idea what vehicle it would power. The answer came hurtling through space. Just 3 days after Noyce and his partners founded Fairchild, the Soviet Union launched Sputnik, the world's first satellite. Americans were terrified. It looked like the Soviets had leapfrogged ahead in the Cold War tech race. 4 years later, they sent the first human into space. The United States was falling behind, and it stung. President John F. Kennedy responded with a bold declaration. America would put a man on the moon. This wasn't just political theater. It was an enormous engineering puzzle. The Apollo spacecraft would need a guidance computer more powerful than anything that existed. But there was a problem. A computer powerful enough for the job, using the technology of the day, would be the size of a refrigerator and would guzzle more electricity than the entire spacecraft could generate. Suddenly, Bob Noyce's expensive little invention didn't look so crazy. NASA realized that Fairchild's integrated circuits were smaller, lighter, and used far less power than anything else available. They bet the entire Apollo program on this brand new, unproven technology. It was a massive gamble. And it paid off spectacularly. The computer that guided Apollo 11 to the moon weighed only 70 pounds and was 1,000 times smaller than the room-sized ENIAC. The space race gave the chip industry its first big customer. The second came from the military. The Air Force needed a new guidance computer for its Minuteman II missile, a weapon designed to carry nuclear warheads across the globe to hit the Soviet Union. The old guidance computer was a clunky beast. Texas Instruments, Jack Kilby's company, promised that a computer using their integrated circuits could be twice as powerful at half the weight. Overnight, the U.S. military became the chip industry's sugar daddy. Fairchild and Texas Instruments exploded, from scrappy startups to booming companies with thousands of employees. But this created a whole new headache. How do you manufacture these insanely complex devices not by the dozen, but by the thousands, and eventually by the millions? The answer was another stroke of genius. An engineer named J. Lathrop, who was working on tiny fuses for mortar shells, had a clever idea. He knew a microscope could magnify small things. What if you flipped it upside down? It could shrink a big pattern down to microscopic size. He coated a slice of silicon with a special chemical called a photoresist, which reacts to light. Then he shined light through a stencil or mask of the circuit pattern he wanted to create. The light passed through the upside-down microscope lens, shrinking the pattern and projecting a miniature version onto the silicon. Where the light hit, the chemical changed and could be washed away, leaving a perfectly carved pattern on the silicon wafer. He called it photolithography, literally, printing with light. This technique transformed chip-making from a delicate art into a mass production process. But making it work at scale was brutal. A single speck of dust could ruin a chip. The chemicals had to be impossibly pure. It was endless trial and error. Engineers working around the clock, constantly tweaking temperatures and pressures, trying to boost the yield, the percentage of chips that actually worked. This is where a new generation of heroes enters the story. People like Morris Chang, a master bridge player who approached manufacturing with the precision of a chess grandmaster at Texas Instruments, methodically experimenting to drive yields from nearly 0 to 25%. And Andy Grove, a refugee who had fled communist Hungary and arrived in America with nothing. He became a tough, relentless production engineer at Fairchild, obsessed with efficiency. These weren't just lab-coat scientists. They were manufacturing wizards who understood that making Moore's Law real wasn't just about physics. It was about mastering the factory floor. What's Moore's Law? In 1965, Gordon Moore, one of Fairchild's co-founders, noticed something incredible. He observed that the number of transistors engineers could cram onto a chip was doubling roughly every year. He predicted this trend would keep going, leading to chips with exponentially growing power. This prediction became known as Moore's Law. It wasn't a law of physics. It was a law of human ambition and economic drive. It became the heartbeat of the entire industry. Double the power at a lower cost per transistor every couple of years. It was a relentless rhythm that would reshape the world. As the industry expanded, it began splitting into two distinct worlds, two competing philosophies. In the Soviet Union, leaders were obsessed with catching up to the United States. They built their own version of Silicon Valley, a secret city called Zelenograd. They even had spies, like Joel Barr and Alfred Sarant, two American communists who defected to the Soviet Union and helped build their computer industry. But the Soviet strategy was fundamentally broken. It was built on a single command from the top: copy it. Soviet engineers were brilliant, but they were ordered to reverse engineer American chips. The problem is, stealing a chip is like stealing a cake. You have the finished product, but you have no clue about the recipe, the oven temperature, or the subtle techniques the baker used. The real secrets weren't in the chip itself, but in the insanely complex manufacturing process. The know-how locked in the minds of people like Morris Chang and Andy Grove. And because of Moore's Law, by the time the Soviets managed to copy a chip, Silicon Valley had already raced ahead to the next generation. The copy-it strategy doomed them to always be playing catch-up. Japan, however, took a completely different path. A young entrepreneur named Akio Morita, co-founder of a small electronics company called Sony, saw the transistor not as a weapon, but as the key to revolutionizing everyday products. He licensed the technology from Bell Labs and, in 1955, created one of the world's first transistor radios. It was a smash hit. This kicked off a new era. American companies like Fairchild and Intel were happy to license their technology to Japanese firms, whom they assumed were years behind. But Japan's real strength was taking that technology and building incredible, high-quality consumer products. They perfected manufacturing and spotted new markets that Silicon Valley had missed. Soon, Japanese firms like Sony and Sharp were dominating the markets for calculators, televisions, and VCRs. This wasn't a copy-it strategy. It was a license and innovate strategy, and it was turning Japan into an economic powerhouse. As demand for chips exploded, another problem popped up. Assembling a chip, the delicate process of attaching the tiny silicon die to its plastic packaging and connecting it with microscopic gold wires, was still done by hand, mostly by women on assembly lines in California. But there weren't enough workers, and their wages kept climbing. Charlie Spork, a hard-driving manufacturing boss at Fairchild, found a solution in Asia. In places like Hong Kong, wages were a tenth of what they were in America. The workers were fast, precise, and, as one executive bluntly noted, more willing to tolerate monotonous work. In 1962, Fairchild opened the first offshore semiconductor assembly plant in Hong Kong. Soon, other companies followed, setting up factories across Taiwan, South Korea, Singapore, and Malaysia. This was the birth of the global supply chain we know today. It was a decision driven purely by economics, but it had huge geopolitical consequences. For leaders in Washington, these new factories were more than just cheap labor. They were a strategic weapon. As the U.S. was losing in Vietnam, there was real fear that countries across Asia would fall like dominoes to communism. But by weaving these nations into America's tech supply chain, the U.S. was binding them to a capitalist, American-led world. For countries like Taiwan, hosting an American chip factory wasn't just about jobs. It was a form of insurance, a silicon shield. While the world was being rewired by these new supply chains, another revolution was brewing back in Silicon Valley. Bob Noyce and Gordon Moore, fed up with the management at Fairchild, left in 1968 to start their own company. They called it Intel. Their first big move was a new type of chip called DRAM, or Dynamic Random Access Memory. Before this, computers stored data using tiny magnetic metal rings, painstakingly woven together with wires. It was slow and bulky. Intel's DRAM chip could store information, the ones and zeros, right on silicon. Thanks to Moore's law, they knew these memory chips would become exponentially more powerful and cheaper over time. They were dead right. But Intel's most world-changing invention came almost by accident. A Japanese calculator company, Busicom, asked Intel to design a complex set of 12 different chips for a new calculator. An Intel engineer named Ted Hoff thought this was way too complicated. He had a radical idea. Instead of designing a dozen specialized chips, why not create one single, general-purpose chip that could be programmed with software to perform many different tasks? In 1971, Intel released the 4004, the world's first microprocessor. It was a computer on a chip. This single invention flipped everything on its head. Before, every device needed custom-designed logic chips. Now, you could use a standard microprocessor and simply write different software for it. The cost of creating smart devices plummeted. A revolution was coming, and as one Caltech professor, Carver Mead, predicted, we have computer power coming out of our ears. Nobody understood the military implications of this better than William Perry. A Silicon Valley entrepreneur who sang in the same choir as Bob Noyce Perry, became a top official at the Pentagon in the 1970s. At the time, the U.S. military felt it was falling behind the Soviet Union, which had way more tanks and planes. Perry championed a new, offset strategy. The U.S. couldn't win on quantity, so it had to win on quality. The key was leveraging America's one massive advantage, its lead in microelectronics.